Let's talk about properties of solutions. So when I have a solvent just by itself, it has its own unique properties. But what happens to those properties when I add the solute particles in? Because once I have other stuff floating around in there, it's going to affect the way the particles of my original solvent interact with each other. So we get our properties of solutions. Now, one of the things that we get electrolytes and non-electrolytes. If I dissolve something in water, that gives me mobile charge. Now I have an electrolyte and I can conduct electricity. And if I put like a light bulb apparatus in there, my light bulb will light up. So pure deionized water, it's not going to conduct electricity. There's no mobile charge. There's no ions. But if I take something like sodium chloride, an ionic solid that's highly soluble in water, and I dissolve that in water, now I'm going to get an electrolyte, because once those ions are dissolved and moving around, positive charges, I have negative charges. I have mobile charge. I can light my light bulb. A non-electrolyte doesn't give me that mobile charge. We don't get any electrical conductivity. Something like sucrose, sugar, that's not going to conduct electricity because sugar doesn't have any ions. It dissolves, sure, but it doesn't give us ions. So we have no mobile charge, so our light bulb won't light up. The other thing we get is what we call colligative properties. When we dissolve something, those solute particles get in the way of the way our solvent particles are used to interacting with each other. And one consequence of this is that the boiling point of the solution goes up from the boiling point of the pure solvent. The freezing point of the solution goes down from the freezing point of the pure solvent. And then we get some effects with what is called osmotic pressure and how things move across a semi-permeable membrane. Okay, so you can look at these diagrams here and you can see that in the pure system, everything's interacting with each other, no problem, totally normal. But in the other system with the little red dots, now I have solute particles that are getting in the way of my pure solvent from interacting with each other normally. And then here we have a phase diagram. Our solid black line is our pure and the blue line is our solution. And so it shifts out, our boiling point goes up, our freezing point goes down. So let's see how this affects. So we're going to take some ethylene glycol and we're going to put it in our radiator. So this is an antifreeze. So if you live in an area or you've ever lived in an area where you get below freezing, we don't have this problem here in San Diego, but other places do. And so you put antifreeze in because the last thing you want is for your radiator block to crack because of frozen water in your radiator. So we want to figure out what our boiling and freezing points are. So we have that generic equation, delta T is equal to K times M, where the delta T of the boiling point is equal to the Kb times the M. The delta T of the freezing point is equal to the Kf times M, where M, that lowercase m, if you remember our solution math, that's molality. All right, so M equals the molality. So we have a kilogram of ethylene glycol and 4,450 grams of water. So we need to do some conversions before we're able to figure out what these new freezing points and boiling points are. All right, so ethylene glycol has a molar mass equal to 62.068 grams per mole. Okay, so we're going to take our 1 kilogram of ethylene glycol times 1,000 grams in 1 kilogram times 1 mole of ethylene glycol in 62.068 grams. And we're going to get 16.11 moles. Okay? And our 4,450 grams is 4.450 kilograms. Okay? So now I can get my molality. So I'm going to take my 16.11 moles of ethylene glycol and my 4.450 kilograms, and I'm going to get a molality of 3.62 molal. Okay? So we have a molality of 3.62. So now we're going to use that molality for both of our calculations. All right, I have the KB listed first, so let's do our boiling point. So our delta, so the change in our boiling point is going to be equal to 0.512 degrees Celsius per mole times 3.62 mole. So the molality cancels, and we get 1.85 degrees Celsius. So this is telling us that the change in our boiling point is 1.85 degrees. That's how much it's going to change. So remember, boiling point elevation. So we're going to take the original boiling point of water and add the 1.85 degrees to it. So boiling point of water is 100 degrees Celsius. So 100 degrees Celsius plus 1.85 degrees Celsius gives us 101.85 degrees Celsius. So this much ethylene glycol in that quantity of water changes the boiling point to 101.85. Now let's look at our change in freezing point. Okay, we're going to get 1.86 degrees Celsius per mole times our 3.62 mole. Again, molality cancels, and we're going to get 6.73 degrees Celsius. Okay? So let's see here what happens. Remember, freezing point depression. Our freezing point is going to go down. The freezing point of water is 0 degrees. So we're going to subtract, because we're going to go down, so we're going to subtract from that 6.73 degrees Celsius. So our new freezing point for this particular solution is negative 6.73 degrees Celsius. All right? So that's our different freezing point and our different boiling point when we make this solution. All right, I have a challenge problem for you. I want you to try this problem. See if you can figure out what the molar mass is. Now remember, molar mass is grams per mole. Using this data, it says that it raised the boiling point of camphor, so the delta TB is 0.114 degrees Celsius, and you have the KB. So if you know the delta T and you know the constant, you can solve for the missing molality. If you have molality and you have the amount of solvent, you can figure out the moles of the solute. And if you have the grams of the solute and you have the moles, you can put grams over moles and figure out the molar mass. So this example problem is no longer an example problem. This is a challenge problem. Okay? Your mission, should you choose to accept it, is to solve this problem. Write out how you solved it using the problem-solving techniques that I have shown you so far throughout this course. Take a picture of it. Email it to me. Send me a message on Canvas, and this will be worth a few points of extra credit. But you have to do it correctly. All right, this is not just a try any old thing, okay? You've got to do the problem correctly. So you can consult with each other. You can email me a final answer and just say, hey, I got blah, blah, blah grams per mole. Is this correct? And I'll let you know if your answer is correct or not. But to get the extra credit, I want to see that you understand how to put all these pieces together and solve it, all right? So that's your mission, should you choose to accept it. All right, the last thing we need to talk about in this section is that osmotic pressure. All right, so we have this equation here, this pi equals MRT, where we've got osmotic pressure, molarity, what we call the ideal gas constant. It's this 0.08206. It has units of liters times atmospheres divided by moles times Kelvin. And then we have a temperature in degrees Kelvin, okay, or in Kelvin. So what happens in osmotic pressure is we have a solution on one side and a pure solvent on the other. So there's a semi-permeable membrane. The semi-permeable membrane allows the solvent particles to pass, but the solute particles are too big. And so what ends up happening is we get a lower concentration of the solvent on the solution side because there's solute particles in the way. And so what ends up happening is the solution, the whole system wants to equalize the pressure. And so it will move solvent from one side of the semi-permeable membrane to the other to get from where the concentration of water is higher to where the concentration of the water is lower. And so the difference between those two is the osmotic pressure. Now, osmotic pressure has some implications in our bodies. So an isotonic solution is normal. We've got great red blood cells at an isotonic solution. Now we have all these salts in our body. And so if we're out of ratio of what we need to be, then water is either going to flow into our blood cells or flow out of our blood cells to try to equalize that pressure. And so hypertonic, we have less water in our blood cells than necessary, and our blood cells will shrivel. Hypotonic, too much water is flowed into our blood cells and they start to swell. And when they swell, they can clog things up or they can burst. And so it's really important to have the right concentrations and pressures on both sides. All right, so let's try this problem right here. So we've got a solution with 3 grams of pepsin. It's a protein. It's really big. It's a macromolecule. There's 10 mils of solution. We've got an osmotic pressure and we've got a temperature. What's the molecular mass? All right, so this is kind of similar to that other problem that I want you to try. So we're going to go through this, and this might help you with the other problem. All right, so we have this equation right here. Okay, so we need to know some stuff. Well, right now, R is a constant. We're given the osmotic pressure and we're given a temperature. What we don't know is that molarity. Okay, so we're going to need to solve for the molarity. So our molarity is going to be equal to the osmotic pressure divided by RT. Okay, so R, remember, is 0.08206 liter atmosphere mole Kelvin. And then we need our temperature in Kelvin, so 25 degrees Celsius plus 273.15 gives me 298.15 Kelvin. Okay? So my osmotic pressure, we're going to take 0.213 atmospheres divided by 0.08206 liter atmosphere mole Kelvin times 298.15 Kelvin. Atmospheres and atmospheres will cancel. Kelvin and Kelvin will cancel. Now, this has liters over moles, but it's on the bottom. So when we solve it, and that goes to the top, it'll be moles per liter, which is our concentration. So what we get is we get 8.706 times 10 to the negative third moles per liter. Okay? So far, so good? That's our concentration. Now we have 10 mils of our solution times 1 liter in 1,000 milliliters times 8.706 times 10 to the negative third moles of our pepsin for every 1 liter of that solution. So we get 8.706 times 10 to the negative fifth moles of pepsin. Okay? All right, we still need that molar mass. Now we've solved moles. Okay? So, oh, and it glitched my extra slide again. Cool. I'll just solve it on here. We're going to take our 3 grams of pepsin over our 8.706 times 10 to the negative fifth moles pepsin, and we're going to get 3,445.89 grams per mole. It's huge because, again, pepsin's a protein. It's a macromolecule. It should have a giant molar mass. Okay? So if you can figure out moles and you're given grams, you can get the molar mass. All right, and then this last image here, this is of a way that they can purify seawater. This is actually called reverse osmosis. And so what they do is they pump seawater in, and then they pressurize the seawater and force the pure water to go through the semi-permeable membrane, trapping the salt on one side, and then pumping the pure water out. This has some interesting problems though, because one, it's pretty energy intensive, and two, once they push all the pure water out on the other side, they're left with a highly concentrated brine on the seawater side. And what do you do with that? Can you put it back in right back in the ocean? Probably not, because that would mess up the balance that's in the ocean. So it's a method. It's got some issues that need to be worked out before it can be used on a larger scale. So these are our properties of solutions.